now we move to our second speaker. Our second speaker is Xianyang Jiang. He's currently a postdoc, also in the Department of Applied Mathematics and Theoretical Physics, DAMP at the University of Cambridge. He completed his PhD only last year from Peking University, January 2020, and his research interest is mostly focused on coherent structures in transitional and turbulent flows. He's currently working in the group of Paul Linden on stratified exchange flows in an inclined block. So Xianyang, floor is all yours for you. Oh.
Okay, thank you for kind of introduction. And can you see my screen? Yeah. Okay.
Yes, perfect.
Okay, thank you. Okay, and thanks to organizers for inviting me to give this talk. And hello everyone, today I'm going to introduce my work on the metamorphosis on the three-dimensional structure in both transitional and turbulent structures, a boundary layer. This work was finished during my PhD in Peking University and under the supervision of Professor Li, and it also co-worked with Dingwei Gu, Professor Smith, and also Professor Linden. Okay, today's topic is actually about the flow structures in boundary layer. And here is a very beautiful painting about flow structures from a wave and its breakdown to small structures like vortices. And another famous about flow structures is vertical structures. That is the main part of our observed turbulence. Okay, and the topics today mainly about transition from laminar boundary layer to turbulence boundary layer. And usually in classical transition, it was initiated by environmental disturbance from 2D TS wave, and it is three-dimensionalized and appearing with vortices. And in the final stage, there will be some turbulence spots and eventually to fully developed turbulence. And these all stages may not be in a specific transition path. So for some case, there will be only TS wave, and in some case, no turbulence spots appears. So the question here is how three-dimensional waves develop into turbulent into vertical structures. And the second one is what is the inception of turbulent spots? And these two questions, what they are relation to related to turbulence. So today's my topic is mainly about transition and turbulent spots and turbulent case. So to draw their similarities. And for classical K-type transition, it's begin with TS wave and aligned hairpin-like structures. It will some interaction between two-dimensional wave, three-dimensional wave, is also oblique waves, and stringwise vortices or streaky structures. And it was observed that the lambda structures here we observed in hydrogen bubble visualization was developing from a kink structures. Here is also termed as soliton-like coherent structure. It's a 3D nonlinear wave packet, can travel a long distance with little loss of energy. And when we observe in side view of these timelines, we see the kink develop from the wall, and it will be a warped wave front. This is three-dimensional wave front, and finally to discrete vortex. So the warped wave front, it means that TS wave warps its front, and finally to be a sweep back front, like this bubble accumulation pattern. And in turbulent spot case, it usually appear in high disturbance, free stream disturbance. And we see here is the temperature field that turbulent spots develop. And when we see the origin of these turbulence spots, it seems they are originate from triangular shaped structure here and the hairpin-like structure. So what's the relationship between these triangular shaped structures and the final turbulence spot? Okay, and in the final turbulence case, in the visualization, we see this is a typical low-speed streak. And it's meandering and also oscillating during the development. And this low-speed streak is also observed in some transitional case. So what's the relationship? Okay, so to answer these questions, we need to visualize the structures. And in this talk, I mainly use the Lagrangian tracking method. We use the data set from transition case or experimental case or numerical simulation case. And we track each particle's development to visualize their development like traditional straight line or timelines and also surface evolution. And then we, based on the trajectory of each particle, we try to extract the Lagrangian-averaged enstrophy. This is an integral of enstrophy over a period of time to see the vorticity concentration or stretching, shear layer. Okay, for K-type transition, here we show nonlinear parabolized stability equation studies. We introduce 2D wave and a 3D wave at the beginning to see what's the difference between K-type transition in zero pressure gradient and also adverse pressure gradient. And this is for zero pressure gradient. And we see here the TS wave three-dimensionalized and to develop hairpin-like structures. And it seems that the lambda structures here is directly developed from the warped wavefront we mentioned before, and the high shear layer is locating here in the front region. But for adverse pressure gradient, it seems a bit different. The helping lambda structures, it seems to develop from a tilted transverse vortex tube. And finally, it will look like omega-shaped structures. But the whole progress is similar. I mean, the pattern of this development. And both the cases are similar to our experimental observation that warped wavefront here and lambda-shaped structures. And the low speed region we see here is also appear in the middle of these lambda structures. Okay, to better visualize the wave development, we also examine the surface evolution at different wall normal position for the two cases. And this is the evolution of surface at the near wall region for zero pressure gradient. We can also see the helping or the lambda-shaped structures develop from the three-dimensionalized wavefront. But for adverse pressure gradient, we see here the surface deformation, and the lower case one is the transparency surface in a different angle to visualize the structure inside this wavefront. And you see that the lambda structures, they develop upward to protrude the surface. So it means here the structures seems to be more closer to the wall, closer to the wall. And to see the vorticity concentration along these structures, we use LAE to visualize the structure development. And here is the triangular shaped structures by the isosurface of LAE. And it's developed to a lambda shaped structures here. And from the contour of this LAE distribution, we see the two regions with a high concentration of vorticity. One is in the lambda structures head, and the other is in near wall region. But for the adverse pressure gradient case, the whole structures look similar, but we see the higher concentration of vorticity at the head and also in the near wall region. It means that there will be more intense localized shear layer near the wall induced by this adverse pressure gradient. Okay, so from the classical transition to turbulent spots, and we want to see what the wave structures play, the role it plays in inducing the turbulent spots. And here we introduce a wave-like disturbance to see how it develops into a turbulent spots. And this is the fluctuation pressure disturbance. And this is the initial form of the disturbance. And the pressure will undergo two stages. One is linear stage, and then is nonlinear stage. And in the linear stage, we see here, there are two wave train here, and they develop downstreams with the roll up occurs at here wave front, and the two weak low speed region here appears. But for nonlinear case, this low speed streak here is more narrow and similar to turbulent case. And in the front of this packet, we see rotational structures here. It's lambda structures here. It means that the low speed streak may not be the result of vertical structures. It can be also results of wave packets. And this packet will finally break down to a turbulent spots. The evolution of material surface near the turbulent spots at different wall normal distances shown here. In the higher position, we can see the wave front and also a very clear three-dimensional wave in the middle. And in near wall region, we see two low speed streak here, and they consist of several three-dimensional wave here. And the LAE distribution also show that the strongest concentration of vorticity is the front region. This means that higher shear appears here. And the contour of this cross section shows that the wave front is the highest vorticity concentration, and another region we can see a weak hump-like structures just at the position of this low speed region. So it seems that turbulent spots is also a result of wave packets. So let's see the turbulent boundary layer. And this data set is obtained by tomographic PIV, and we focus on near wall region that Y plus is below 100. And we reconstructed the low speed streak development here, similar to hydrogen bubbles visualization. and identify the low speed strike and their development. Here, the low speed strike are similar to hydrogen bubble visualization with span-wise spacing is almost Z plus is about 100. And if we place a particle at the region of low speed strike, and this particle will develop a strike line, just like an oscillation of waves development. And the three-dimensional timelines also show the amplification and the damping of the wave structures. So when we trace the surface development in the low speed region, it also looks like a wave amplification. That surface are lifted up at low speed region and are swept down. I mean, they are more closer to the wall at the high speed region here. And if we extract one surface, we can see it consists of two waves of this surface. It seems that low speed strike also consists of wave-like structures in this low Reynolds number turbulent boundary layer. And when we examine the vorticity concentration, we see that this isosurface of LAE show a stringwise vortices, and they are located at the region of high-speed strike, just at two sides of low-speed strikes. Okay, according to our observation of these three kind of flow from transition turbulence spots and early turbulence, we proposed a conceptual model here. When there is a 3D wave, either soliton-like coherent structure or warped wave front, it will lift up to form a low-speed strike. Here, low-speed strike is a general concept that is low-speed region, and the low-speed strike will create vortices because of its instability, like varicose or sinuous instability to finally to induce the stringwise vortex or helping vortex. And with the presence of vortex, it also induces low speed strike because of a lift up mechanism. And there will be interaction between these two structures. Like the work of Zhao, they show that interaction of helping structures and low speed strike will finally form a turbulence spot. And according to our study in transition, K-type transition, we see the warped wave front is the origin of the lambda structures. So from wave to vortex, and also there is some interaction between wave and vortex according to our mentioned wave resonant interaction. And with these three kind of structures, they have some interaction and induction. So there will be a self-sustaining process similar to a concept proposed by Valif. And also the vortices will induce turbulence spots because of its laterally and stringwise spreading or regeneration. And there will be interaction between strike and spots in many studies. And in our work here, we see that 3D wave packets can be broken down to turbulence spots. And with the turbulence spots and the vortices, they will finally lead to a turbulence. So this is a conceptual model based on our observation. So here is a conclusion that we see in transitional boundary layer that lambda vortex developed from a 3D warped wavefront. And with the presence of adverse pressure gradient, warped wavefront or lambda vortex undergo a more rapid revolution and a stronger stretching near the wall. And also we see wave packet also contribute to an inception of turbulent spots. And there's a similarity of flow behaviors between these transitional and turbulent boundary layers, mainly by the wave front or wave-like structures. And we propose that the amplification and the lift up of this 3D wave will create high shear layer that lead to rotational structures and turbulence. I'd like to thanks to my collaborator, Professor Chenbiao Li from Peking University and Professor Smith from Lehigh University, and also to Professor Linden, University of Cambridge, and Dr. Xi Chen for providing a NPSE dataset, and Gu Dingwei for providing data, and also Junwei for providing assistance in tomo PIV measurement. Okay, thank everyone for listening.
Thanks so much, Xianyang, for the beautiful, impressive talk. About your experimental method, your tomographic PIV system. So you showed half a slide about, it looked like a multiple camera. Can you have a slide, or can you elaborate a little bit on the technique that you use for those measurements?
Okay, thanks for the question. In tomo PIV measurement, we use the commercial software from Lagrangian, and they provide the software, but we integrated the system from we bought laser and cameras and integrated it together, but we controlling in software and post-processed by the software of Davis. Yeah.
I see. Which I guess answers the next questions. That is, thanks for the impressive talk. What tools did you use for post-processing? Which I guess you just answered. Okay,
thanks for the question. I mainly use MATLAB for post-processing, providing the three-dimensional dataset, and I can use the MATLAB to track particles. But because we use Lagrangian tracking, we only consider a period of time. So we don't need to track particles to very long time. If the particles propagates out of the window of our measurement, so we can stop there. So it's save the space of the tracing. Yeah, so mainly by MATLAB.
I see. Thanks. Next question says, do you consider the turbulent intensity?
Okay, thanks. Turbulent intensity is very important actually for transition. And here in my transitional study is mainly by numerical simulation, and we didn't change the turbulent intensity because we only introduce the 2D and 3D waves. But for turbulent case, we measured, in our measurement, the turbulent intensity is about 0.7%. And yeah, but we care about the turbulence, so we didn't change the intensity.
Is the conceptual models only suit for natural transition?
Thank you for your question. I think this is an ideal model actually. And in natural transition, it means that TS wave or oblique wave place. I think it's because we focus on three-dimensional wave. So I think it is suited for natural transition. But for our case, the three-dimensional wave may not be a result of TS wave. It can be other kind of disturbance. So in that case, I think it can be also suitable because with the presence of three-dimensional wave, its lift up or amplification will induce a high shear layer, and the story follow that will be similar, I think. Yeah, but this still need to be verified, I think, in many different areas. Yes.
Okay. That's clear. There's another question just popped up. So it says, thank you for a wonderful presentation. I'm wondering if there is a way to differentiate the linear versus non-linear transition regions during the transition.
Okay. In the traditional way, we see the natural transition case, the linear case, we usually focus on the development of, by normal mode evolution, TS wave. But in the nonlinear case, it's usually the three-dimensionalized of TS wave and the appearance of vortices. But I think you may also mean nonlinear and linear in our turbulence spots case. In that case, we identify linear and nonlinear by the pressure disturbance development. So we see is linear development, so we to identify their linear stage.